Okay, so let's get started. So today I'm going to talk about the third of the classical control modes, which is derivative mode control, and then kind of just briefly describe the mixed mode, which means you're mixing together P, I, and D control. And as I mentioned, this is basically what you can buy in the market. You go and buy a PID controller. It has all three modes of control. And then this gives us the basis to go into a little bit more advanced concepts of a cascade control and the effect of delays. Talk about that. And then stability is a fairly large topic. So I'm going to start with the introduction to stability and give an overall intuitive understanding of stability. And then we'll go into the more mathematical background of stability and poles and Lyapunov stability on Monday. Okay, so let me just start with the basic derivative mode control. So by now you've seen the feedback loop many times, so I'm not going to repeat it. But I'll just indicate that if you just remember, for proportional mode, we have the control U equals Kp times the error E. This is in the transform domain. In the I, we have U equals Ki E over S. So where the 1 over S is the integral mode. And in the derivative mode, we have the control to be just Kd, which is the constant Kd, SKDE, where you recognize that the multiplication by S corresponds to the derivative operation in we'll not come in, it's your chair is right there. And so in the D mode, we are going to see the control in the form SKDE. Or maybe you can think of it as KD times SE, where SE is SE corresponds to the Laplace transform of dE by dt. In the notes I made a mistake. I said dE by ds. It's actually dE by dt. Okay. So the derivative mode control, what it's doing is that it's basically saying that the control action must depend not only on the magnitude of the error, but at the rate at which it's increasing or decreasing. Okay. And I guess I'm going to try and use since it's cold outside, I'm going to use a control loop from tobogganing. So how many of you have been out on a slope, on a toboggan? Okay, only a few of you. Well, don't worry, but next month you'll all have a chance to do it on your way to work even. But actually, if you just cross Columbia on the other side, there's a field and there's a little bit of a slope, and I take my kids there once or twice every winter, and you go straight down the hill. So in toboggan, you have an input. Input is you have actually all you have is a brake pedal. You can't really go faster. You can only go slower by pressing on the brake pedal. So you have some optimum speed at which you want to go. So of course, for my kids, the optimum speed is infinite. So they want to go as fast as they possibly can. But I am less keen to go fast. So I have my brake pedal, and whenever it goes too fast, I put the brakes on so that I don't kill myself. Imagine that you put the brakes on, but the error is, so you're going much too fast, and you put the brakes on, but the speed isn't decreasing. Okay, so in some sense, the speed increases. So you have a large magnitude error, you have large control action, but your error is still increasing, it's still positive, right? The rate of growth of error is positive. So in some sense, what you have is that you have over here, let's say this is time, this is the error. So the error is increasing in magnitude. At some point you say, look, I really need to take control action. You take control action, but yet the error is increasing. So at this point, you should be worried, okay, because your brakes are basically not working. So you want to do something, even more dramatic, like fall out. And so this corresponds in this zone to having dE by dt is greater than 0. Okay, so that's basically what you're saying is if the error is still going up or error is large, then I should be careful, I should do something more drastic, and that's where you have this SKDE or dE by dt because it's positive. On the other hand, what happens is that let's say you applied the brakes and the error is dropping pretty fast. So the error magnitude is, let's say the error magnitude is some value over here, but it's dropping fast, okay? So at this point in time, you're saying, look, my control action seems to be doing pretty well, okay? It's doing a pretty good job, and so the error magnitude is dropping. So because it's dropping, I probably don't need to have such a strong degree of braking anymore. I can ease off on the pedal. Or more intuitively, maybe I should draw it like this. Suppose I were to draw this line over here, okay? And now consider this path over here versus this part over there, okay? The magnitude of the error is the same. So if you're doing proportional mode control, my KPE, okay, is going to be the same in both cases, right? Because the magnitude of the error is the same. However, in this case, my error is going up, and in this case, my error is going down. Intuitively, it makes sense for me to ease off on the control at this point and actually increase my control over here. So if I had only proportional mode control, I would not be able to do that. I would be kind of forced to use the same exact amount of control over here and over there. Okay, whereas in the derivative case, I can be more aggressive here and less aggressive there. Okay? So hopefully that kind of explains what's going on. So this is also what we call a feathering in. You're kind of easing off on the control if things are going well, and you're pushing harder when things aren't going well. And that's the gain you get from derivative mode control. Okay. Any questions about that? Okay. Okay, so maybe actually I should put that in my should put that in the text. Let's see. So derivative mode control. Okay, good. So, okay, so let's look at it more mathematically and see what the derivative mode control looks like. It's actually pretty straightforward. So we're going to look at the web server example. And the web server, we have very simple plant, G equals 1 over S. And as before, now we're going to do U equals KD for derivative, okay, E S, which is going to be KD R minus Y S, okay. And and this is because that's the error. Now we know that so Y is going to be equal to 1 over S U minus W, and so substituting for U over here, we get Y equals 1 over S KD R minus Y S minus W. Okay, so this is where, so Y is basically equal to G U minus W, right? So this is pretty straightforward. This part is just the definition of U from derivative mode control. This part is just Y equals G times U minus W. That's the web server model. And then we're just substituting for U as KD R minus YS. It's exactly that. So there's nothing really complicated going on. When you rearrange this, we get Y equals KD over 1 plus KD R minus W over S, and there's a mistake over here. It should be 1 plus KD as well. So I made a mistake in the, there's a typo there. So that should be 1 plus KD in the denominator. So I think Leela caught that, so thank you. Okay, so to study the step response, we, as usual, what we do is we substitute R equals 1 over S and W equals 0, in which case we get Y equals KD into S 1 plus KD. Okay, and we want to look at the behavior of this. So if you find the inverse Laplace transform, YT becomes just basically 1 over S goes to 1, right? 1 over S goes to 1. This is a constant. This whole thing over here in this box is a constant. So this YT is just KD over 1 plus KD. That's it. So it's just a constant value. Okay, so you give it a step input, and it's going to give you output, and the output is going to be slightly less than 1. It's KD over 1 plus KD, which is always going to be a value that's less than 1, when KD is greater than 0. So that basically tells us what the output is going to look like. Now, if you look at the steady state error is going to be given by, we can basically see that we're giving it an input of 1, okay, and the output is KD over 1 plus KD. So 1 is something like that, KD over 1 plus KD is something like that. So it's always going to be a steady state error because the input is 1 and the output is this. You can also look at the final value theorem. Yeah?
R is 1 by S, right?
R is, sorry, 1 by S, I'm sorry, yeah. Yeah, I'm sorry, yeah. So you get the 1 over S over there. And so you can see that the final value theorem will also tell us that the steady state error is non-zero, okay? So that's the problem with derivative mode control. So actually there are two problems. One is that the steady state error is not 0. So we want the output to look like 1. In the proportional mode control, we had basically yt look like, so 1 minus e to the minus something, right? So that eventually gets to 1, which is good. But here we have always going to have some error, okay? And so that's not good. And in fact, what we want to do is to use differential mode control in conjunction with other modes of control. Okay, I'll come to that in just a minute. So the problems with derivative mode. One is there's a steady state error. And the second one is sensitivity to noise. And the second one actually is the bigger problem. Because if you look at this graph over here, I showed a fairly smooth curve. Let's suppose that has shown green what might actually happen. Let's say that for some reason I have a spike like that, okay, or some other spike like that. What's going if you look at this part over here, in this part over here, these error suddenly shoots up and then drops down. It could be a measurement error, okay, or it could be that for some reason you hit a patch of ice, okay, and your toboggan went very fast and then slowed down again, okay, so your error suddenly went up and went down again. So you could have that, right? And if you're sensitive and you're seeing this, you're going to see the error suddenly shoot up. When the error shoots up, if you have 0 delay, you're going to have a very large control response. Okay, you're going to say, oops, I'm in really big trouble, and you really respond to that big time because the derivative is very fast. In fact, if you have a noisy system like this, so let's say your error looks something like that, okay, you're going to have lots and lots of very high control actions at each of these points going up and going down. So you get this fluttering effect, okay, and that's not good, okay. You can imagine any control system where you're going to have dramatic changes in control action is just not a good idea. Imagine again, if you're driving a car, your steering wheel is going back and forth like this. That's not very good because you're basically haven't come into this, and we won't talk about this now. We'll talk about information theory. But each control action requires power. Okay, each control action requires some energy to be expended, and if you're just doing this all the time, you're going to tire out your arms, right? That's the energy they're expending for no good reason, okay? And so we don't want to be too sensitive because there's a power constraint as well. And so what we really do is that when we're using derivative mode, we're going to smooth this out somehow. And by smoothing this out, we'll get rid of all those the high frequency coefficients. So if you look at this, what we're really saying is that if you do a filter, a low-pass filter, and by low-pass filter I just mean, for example, a moving window time average. So you take the average of the few values. Okay, let's say you have a system, you just take the average of these values and you just move the window and you just take the average of the values in the window. That's a moving average. Okay, and if you do that, you'll find that you'll get rid of all the high frequency stuff because basically things are going to cancel out in that window. So that's called a low-pass filter. The simplest low-pass filter is just averaging over some window of, let's say, 10 values or 20 values. And you just move the window, you drop the last one, you put the new one in, average it out. That's a moving window. And there are more complicated things you can do, but that's the easiest one. And if you do that, you get rid of all the error, so the spikiness in the error, and then you can get rid of sensitivity to noise, and then you can use the smooth value into your control system. Okay, so that's basically how we really use derivative mode control. Now, before I stop or before I forget, I'm going to. Okay, are there any questions about this? Before? Yeah.
So for problem 1,
yeah.
can you sort of compensate for that by sort of tweaking the reference value?
You could do that. You can certainly tweak the reference value so that you are saying the set point. You're basically, 1 is sort of your command, right? And you're saying the output meets the command. You can say, I really wanted 1.2, and you'll get to 1. So you can compensate for that. And those are called compensators, actually. And they're pretty widely used. But this one is a problem. So steady state error you can compensate for, because you know what the steady state error is going to be as a function of the loop gain if you know the system model. So yes, you can absolutely do that. Because it's a constant offset, right? So we know how to get rid of that. All right, let me look at the homework problem. So there, let me just, I'm just going to sketch it out. So y equals g u minus w, and which becomes 1 over s plus alpha. So we have this new alpha term. And I had given you the value of, where I said the feedback k d was 2.5. So it's 2.5 r minus y s minus w, and this s is because it's derivative mode, and then this becomes y 3.5 s plus alpha over s plus alpha equals 2.5 s over s plus alpha times r plus something in w, which is not really important, because we're going to set that to 0. When you set that to 0, we get y equals 2.5 by 3.5 over s plus alpha by 3.5. Okay, and then when you take the inverse transform, we get yt equals 2.5 by 3.5 e to the minus t alpha by 3.5. So this is really the solution that I'm looking for. So I was looking through the answers you guys gave me for the problem set on Wednesday, and I was amused to see the answers. Some of them were giving the time domain convolution of the input and the system, and saying here's the convolution, it's A convolved with B. Okay, it's correct, but it's not really very nice. You haven't even done the Laplace transform. Other people have given the answer as Laplace inverse of this messy looking thing, saying yeah, it's somewhere there, and that's the answer, so go figure it out. Okay, I don't want me to figure it out, I want you to figure it out. If you're getting an answer like this, the correct grade to give is like, fractional, 0.1 or 0.2 out of 1. Okay, if somebody just says it's, xt convolved with g of t, okay, and just writes xt and gt, the correct answer for that's correct. So you can't give 0, but it's kind of, not, you shouldn't be giving full marks for that either. That's why I specifically stated I want yt. I don't want this convolved with that and Laplace inverse of that and all this other stuff. I want this. Okay, so if this is not the answer, you should give it not give a full mark. And for the final value of the error, or the final value of the error, you want limit t tends to infinity e of t is going to be limit s tends to 0 of s e, which is going to be limit s tends to 0 of 1 minus 2.5 s by 3.5 s plus alpha, and this is going to be equal to 1. So the final value expected of the error is 1. Okay, so we're going to basically we're going to have a steady state error. Okay, what we want is the steady state error to be 0, and with this the final value of the error is going to be 1, which is not 0, and so that's the solution. Yeah. Over here, that's the system model. We have u minus w because we are modeling the drain of the web server as a minus w. Okay, so that's the modeling. Okay, yes, but generally speaking, you would say u plus w and w would be negative. I'm just taking it minus w in this case. But yeah, the standard form is u plus w. But for the web server, because of the funny modeling, it's more intuitive to use minus w in this case. Okay, let's take a break, and after the break, I'll continue with mixed mode control. Yeah, sorry. I'm looking for the steady state error is what happens to E as E goes to 0, or you can see 1 minus y. Either way is fine. I mean, 1 is the command for a step input. So 1 minus y would become 1 over s minus y in the transform domain. So, okay, limit t tends to infinity, okay, 1 minus y of t, okay, is the same as limit t tends to infinity of e of t, because the command input is the step input, which is 1 of t. Right? So if I take the Laplace, I can take the Laplace of e, capital E, or I can take the Laplace of 1 over s minus capital Y. The same thing. It's going to get the same value anyway. Yeah. Any other questions about this? Yes. Yeah.
Y of t, but with Laplace transform, we also have u of t will be not floating up, right? Because it doesn't matter if it's positive time.
Oh, that's right. Yeah, we are assuming it's all causal systems. So basically in this control theory, we're looking only at positive time. We're never looking at negative time. So all the transforms, we were careful to explain positive time versus negative time, all this other stuff. But when you do control theory, we know all the signals are real, and all signals are causal. We don't have anything before time 0, and we never have any complex. Because in reality, we don't have complex signals. Complex signals is just a modeling assumption that we make. So yes, you're right, that UT kind of thing is also good. And also, another assumption we'll always make is that the system value at 0 is 0, initially at equilibrium. Okay. So in the final, it looks like it's still finally the 7th. There seems to be every date has problems, as far as I can see. The 7th has some advantages because then people who want to leave can leave earlier. So, okay, I'll keep it there unless there's an overwhelming change in the doodle, which, okay. All right, let me talk about combined mode or mixed mode. So the interesting part about PID control and why it's really quite easy to use is that everything is done through just 3 constants. The Kp for the proportionality, the Ki for the integral mode, and the Kd for the derivative mode. And that's it. You just have Kp, Ki, Kd for your 3 modes. And so you can essentially set these 3 knobs and get what response you want. And so we can define a mixed mode where the U is going to be, the control action is going to be Kp plus Ki by S plus Kds times E, and this is basically a mixed mode control. Okay, we have the 3 constants. And so what we want to do is to choose these constants carefully, and this is done through a process called tuning. So in the real system, you get the mode, and what you do is, okay, you say, if you have a particular amount of error, how much you want to use for the proportional mode, and you use the Kp, and that controls for the error. And then you say, oh, wait a minute, I don't want to have the same amount of control whether it's going up or going down. So then you'd use the Kd to compensate for that, like we talked about. And then what Ki does is that Kp only acts if the error is non-zero. If there's no error, Kp is not going to have any control action at all. And so if the Ki works on accumulated error. So if there's any accumulated error left over, then Ki is going to get rid of that because you accumulated a certain amount of error. And so the reason why you want to worry about this is because you may want some control action even even if there's zero error, you still want to have some control action. And so you can't do that with this proportional mode, so you use the integral mode, and then you can use the differential mode. So there is quite a bit of, I won't say theory, but rules of thumb, if you wish, on how to choose PID controls properly, okay, which will say first do the proportional mode, then do this other mode, then do the integral mode, then do the derivative mode, and how to adjust these things. And this is more or less, I would say, seat of the pants, or maybe I should call it skilled technician kind of thing. This is the kind of thing that somebody would do when they want to tune your car for maximum performance. Turn this knob, and then when the knob is over here, turn the other knob here and the other knob here, and you'll get something that works. So that is well understood, and it's more in the realm of technology and art rather than science. So I'm not going to go into it, but this is something people use daily. So if you say here's a PID controller for an engine or for a chemical process or for anything, there are rules of thumb, techniques which you can use in order to choose these values. Okay, and that's one reason why it's very popularly used. So I'm not going to. So anyway, so you can look more into that if you end up having to use a PID controller. So at this point, what I really want you to take away is that, well, a couple of things. One is that this is the most intuitive and basic control, PID control. Okay, so if somebody says, what's a PID controller, you pretty much know exactly what it is. And hopefully you also understand at some intuitive level what each mode is doing, what are the problems you can have with each mode. Here's sensitivity to noise, here you have oscillation, here you have no control action when the error is zero. So we have some problems, we have some uses for them. Looking back, the reason why you had to study all the transform domain is because without that you really have no idea what this equation even means. Right? This equation actually is a transform domain equation. It's not an equation in time domain. So if I were to tell you, I want to teach you PID control and I'll show you this equation for mixed mode, this actually has no meaning whatsoever. Okay? So to understand this, you need to understand Laplace transform. Okay? And you need to understand that S times KD means derivative, this means integral, right? I mean, to you, by now, hopefully it's obvious to you, yeah, sure, if I multiply by S, I get derivative, but it's not obvious. Going backwards to understand Laplace transform, you need to understand Fourier transform, okay? Because the Laplace is sort of a Fourier transform with the pre-multiplication to get the absolute integrability constraint. And to understand Fourier transform, you need Fourier series. And to get there, you need to understand what a signal is, and you need to understand what a real LTI system is. And at some level, you start off by saying, okay, what is a signal? What's a discrete signal? What's a continuous signal? And what's a delta? And how delta plays into convolution? Because this analysis is basically assuming that this over here is our system D, and that's the input xt, right? Is E actually is x is the Laplace transform of the xt, and this is the D is our signal. So we are implicitly making the assumption that the convolution in the time domain is a multiplication in the Laplace domain. And so all of this goes back to understanding what convolution is. So what we started out about, I don't know, 5-6 weeks ago with convolution and so on, it's all building up to the point where I can write this equation and you know what it means. Okay, so that's why you went through all that work, so you can get here. And this is, of course, for continuous time control. Similar kind of thing can be said for discrete time control, where you use a Z transform, and similar kind of equations will show up. And we'll study that in about, at the end of next week, we'll look into discrete time. But for now, I just wanted to explain, this equation, why this equation takes a long time to get to. And you look at it and say, oh yeah, sure, that's straightforward, there's nothing here. Okay, but there is a lot here. I can't explain this to you without doing all the prior work before it. So, okay, so hopefully you should feel good about it, that if you understand this equation, you should feel good, because it takes quite a bit of time to get to the stage where it's easy to understand. Okay. Any questions about this? Okay, so now we are sort of at the peak of what I want to get in control theory, and after this we're just going to, it's all easy stuff more or less in the sense that with this concept there are no more conceptual hurdles really, but just building on what you know. And so we'll first look at this notion of cascade control and delays using this as a basis, and then we look into stability, and stability is a very important concept, and I'll first go into the conceptual notion of what stability is, and then we'll do the math. So let me first start with cascade control, and to introduce this I want to first talk to you about a very, very important concept which is called time scale of control. Okay. And time scale of control is something that most textbooks really don't talk about in any great sense, but when you build any real system, this becomes supremely important. And so I'm going to explain it to you in a way that hopefully makes sense. So how many of you have ridden a bicycle? Okay. All right. So all of you ridden a bicycle, I hope. Anybody who has not ridden a bicycle? Okay, good. So that's excellent. How many of you have ridden a bicycle in a crowded place with lots of people around? Okay, walking people. Okay, most of you, right? I hope. So again, I should probably invert the question. So, has anybody not ridden a bicycle in a plaza where there are a lot of people and you kind of have to go in and out through them? No one. Good, because this is important. I do this every morning on my way to work. So when you're on a bicycle and you're going through the crowd of people, right? Basically, the crowd of people are essentially static as far as you're concerned, because you don't have to worry about them moving very fast, because at their rate of walking, you're going about 5 times faster. Okay, the ratio of walking to bicycling is the same as the ratio of cycling to travel by car, roughly 5x each time. So when somebody is walking, for you, they're basically static obstacles, unless somebody raises their arm like this suddenly or shifts like this dramatically, which is terrible because you're going to bump into them. From your perspective, they're static. You can just weave right through them. Okay. What's going on is that you and the pedestrians are at different time scales of control. Okay. From your perspective, they're just static. Okay. So if you want to write the equations of motion that control your motion, you can treat all of them as constants. They're not constants, obviously they're moving, but you can treat them as constants. Okay. So we call this phenomenon a time scale separation. Okay. So the time scale separation tells us that we can essentially treat even things that are variable as constant from the perspective of a faster time scale. Okay, because it's happening so much faster or so much slower. And so when you have a control system, what we want to do is to look at the system and identify its inherent time scales. Okay, at what time scales do things happen? And then you want to basically assign controllers to different time scales separately, and then you want to do something which is, you want these, let's just take the case with 2 time scales. There's a slow time, it's a slow time scale and a fast time scale. And what you want to do is you want the fast time scale controller to be given an input from the slow time scale controller. So let's call this CF and CS. And what the CF is doing is it's giving a control command to the fast time scale controller. Okay. So again, going to the bicycle example, in the bicycle example, we have essentially got 2 aspects to it. On the slow time scale, we want to get from some source to some destination. We want to go somewhere, right? And the fast time scale, you want to avoid all the people in the way, right? So in the fast time scale, you're just told, okay, avoid these people, and in the fast time scale, the people are essentially invisible. They just become constants. You just navigate around them. Okay. And in the slow time scale, you said, okay, go from DC to the ring road, from ring road go there, so that's the slow time scale control. So at each point in time, the fast time scale control doesn't have to worry about navigation, where it's going. It just needs to worry about not hitting the pedestrians, which is really easy, because they're not moving compared to you. Okay. Because if I were to give you the whole problem in this form, I were to say, drive your bicycle from here to there, and there's 1,000 people along the way, avoid all of them and get to the destination, which requires all these complex turns, it's confusing, right? How do you deal with all the people and also